Hello there, Mr. Sutton here with the AB Calculus 4-4 Extra Practice Number 2 solutions on concavity. On this problem, we're trying to find the concavity of this polynomial. So for that, we're going to need the second derivative. So let's do the first derivative now. We've got 6x squared plus 42x plus 36. And now we need f double prime, which is going to be 12x plus 42. To figure out concavity, we need to know critical values, so let's set this equal to 0 and solve it. If I subtract 42 and divide by 12, negative 42 over 12, I guess I could reduce that to negative 21 over 6, or negative 7 over 2 if I reduce that even more. So now let's put this critical value on an f double prime number line and do some testing. A number to the left of negative 7 over 2, well, how about negative 4? So if I plug that into f double prime, this is negative 48 plus 42, which is negative. And now a number bigger than negative 7 over 2, like 0, that would be just 0 plus 42, which is positive. Since f double prime is positive over here, that means that f is concave up from negative 7 over 2 to positive infinity. And since f double prime is negative to the left here, that means f is concave down from negative infinity to negative 7 over 2. To figure out the concavity of this function, we need to find critical values of the second derivative. So let me take my first derivative, and even before I do that, let me rewrite this as x plus x to the negative 1. So now first derivative, using the power rule, we've got 1 minus x to the negative 2. And then we need to go one more derivative. So this 1 gets zeroed out, and we have another power rule here. This is going to be 2x to the negative 3. Now, in order to solve this for critical values, I'm going to rewrite this as a fraction, so 2 over x cubed. And looking for places where this equals 0 or is undefined, I notice that I have a constant in the numerator, so this will never actually equal 0. But f double prime does not exist at x equals 0, because that would zero out our denominator. So that's at least a critical value that we can use. So here's my f double prime number line. We have 0 as our only critical value here. Testing a number less than 0, like negative 1, and we're using this, I'm going to use this f double prime fraction here. So that's going to be 2 over negative 1, which is negative. And then let me test a number bigger than 0, like positive 1. Well, that's just 2 over 1, which is positive. Since f double prime is positive after 0, we can say f is concave up from 0 to infinity. Since f double prime is negative before we get to 0, that means f is concave down from negative infinity to 0. For this problem, I'm trying to figure out intervals of concavity for this polynomial. So for that, I need to know the second derivative. Let's start with the first one, though. That would be negative 6x squared plus 12x, and then that 3 gets zeroed away. Now for the second derivative, that's going to be negative 12x plus 12. And at this point, I need to set this equal to 0 and solve for critical values. Subtracting 12 and dividing by negative 12, we end up with x equals 1. So that's our only critical value. Here's an f double prime number line to put that on. And let me do some sign analysis. Let me test something to the left of 1, like 0. So I'm plugging that into this f double prime formula here. If I plug in 0, that just leaves me with 12, which is positive. And if I plug in a number bigger than 1, like 2, well, that would give me like negative 24 plus 12, which is going to be negative. Because f double prime is positive in this first interval, we can say that f is concave up from negative infinity to 1. And because f double prime is negative in the second interval, f is concave down from 1 to positive infinity. To find the concavity of this quartic function, we need the second derivative. So first derivative first, we've got power rule here, so 4 times 1/4 cancels. We just have x cubed for that first term for f prime, and after that we're going to have 4x. Now for f double prime, that's going to be 3x squared minus 4. And I need to set this equal to 0 and find critical values so I can do some sign analysis. So setting it equal to 0, if we add 4 and divide by 3, that's 4/3, and then the square root of that is going to be plus or minus 2 over radical 3. So let me put this on a f double prime number line. So I'm gonna simplify this as well. So we're gonna have negative 2 radical 3 over 3, and then this will be positive 2 radical 3 over 3. And now I'm going to test a number in each of these intervals. Now, it's a little tricky figuring out a number that's less than negative 2 radical 3 over 3. I mean, you could test negative 1,000,000 and that would work fine. But if you think about this now, the square root of 3, since it's less than the square root of 4, is going to be a number that's less than 2. And if you multiply a number that's less than 2 by 2/3, you get a number that's even smaller than 2. So that means negative 2 is going to be further away than this number here. So negative 2 is less than this number. And if we plug that in to f double prime here, that's going to be 3 times 4 minus 4 is going to give me a positive. Now, figuring out a number between these two critical values is pretty easy. I mean, between negative and positive, you've got 0. So that's just going to be negative 4 for f double prime if I plug it in, which is a negative. And then positive 2 is further away than 2 radical 3 over 3. So if I plug that in, I've got, again, 12 minus 4, which is positive. All right. So because f double prime is positive in the first and the third intervals there, that means that f is concave up from negative infinity to negative 2 radical 3 over 3, union 2 radical 3 over 3 to positive infinity. And because f double prime is negative in between those critical values, that means f is concave down from negative 2 radical 3 over 3 to 2 radical 3 over 3. On this problem, we're trying to figure out intervals in concavity for this rational function. I hope you packed your comfy shoes for this marathon. Here we go. So to get concavity, we need to talk about the second derivative. So let's start with getting the first derivative. And we already see that's going to be a little bit of a pain. That's going to require the quotient rule, u prime v minus uv prime over v squared. Let me use the box and ribbon to help figure that out. So I have my numerator, x squared, denominator, 4x minus 8, and the derivatives of those, which are 2x and 4. Using the ribbon to multiply things out, I'm just going to distribute right away here. So this is going to be 8x squared minus 16x, and then going the other way, we're doing minus 4x squared, all over 4x minus 8 quantity squared, just using the quotient rule. And I'm going to need another derivative, but before I take that, let me simplify this a little bit, make my life a little easier. 8x to the second minus 4x squared, that's just going to be 4x squared, to go with that negative 16x up there. And we could probably even simplify a little bit more. It looks like there's a 4 that could be canceled out in some way, but I don't want to mess around because this stuff is inside of squared parentheses. So let me just go ahead and take another derivative. So f double prime now is going to require yet another quotient rule. So let's go ahead and do that. Box and ribbon time again. We've got 4x squared minus 16x in the numerator this time around. And in the denominator, a little bit more now. This is going to be 4x minus 8 squared. So for the derivative of this first expression, the numerator, that's going to be 8x minus 16. And this derivative here, this is going to be a chain rule, or at least you could do it with the chain rule. We have the derivative of something squared. That's going to be 2 times the something. But now we have to multiply by the derivative of the something, which is 4. All right, so now using the ribbon to put all that together, and I'm just going to write things out initially here. I'm not going to distribute. So we're going to have 8x minus 16 times 4x minus 8 quantity squared. And then going the other way, we've got 4x squared minus 16x in a parentheses times all this stuff. And I'm going to make the 2 and the 4, I'm going to multiply those to get 8, and I'm going to subtract all of that. So we've got minus parentheses this stuff, and then this is going to be 8 parentheses 4x minus 8. And then all of that is going to be over 4x minus 8 squared, which is 4x minus 8 to the 4th. All right, well, this is a big mess. Before we try doing sign analysis and even setting this equal to 0 and figuring all that out, let's see how much we can simplify this. It really helps to simplify before you try solving things. So one thing I noticed right away, and you might miss it if you weren't really looking for this 4x minus 8 gets repeated an awful lot. We got 2 of these in this first term, we've got 1 of these in the second term over here, and we have 4 of them down here. Well, I can cancel out one of those 4x minus 8s from everywhere because they all have at least one of them. So I'm going to do that. That leaves me with 8x minus 16 times 4x minus 8. And over here, this 4x minus 8 cancels out completely, leaving me without that in the second term. And now downstairs, I've got 4x minus 8 to the third power. Now, this doesn't seem like a huge win, but not having that term, that factor in the second term is actually a pretty big win. And even in this first term, now we can actually FOIL this out, distribute this out, without having to worry about this second power here. So a little bit of a win. Let's go ahead and simplify a little bit more, though. So for these left two parentheses, I am going to distribute. So that's going to be 32x to the second. And then the outers, that's going to give me 64x minus 64x. And then this is going to be, let's see, 16 times 8. That's going to be 128. Is that right? I believe so, yeah. So positive 128. And then we have to distribute this 8 to this negative parentheses. So I'll just think of this as a negative 8 that I'm distributing. That's going to be minus 32x to the second plus, this is going to be 128x. And if you look carefully, there are definitely some like terms that we can collect. 32x squared and negative 32x squared, those conveniently cancel out. We have a negative 64x minus another 64x. That's negative 128x, which conveniently cancels out with this positive 128x. Well, how about that? So when the dust settles, the only thing left standing in the numerator after all of that is 128. And the denominator is still unchanged. But I think you'll agree this is a much nicer fraction to deal with now. All right, so now I have to actually find critical values. I haven't even done that yet. I have to figure out where this fraction is either 0 or undefined. Let's start with 0. Since I have a constant in my numerator, this was another benefit of this simplifying. Since I have a constant up here, that means that this cannot equal 0. This fraction will never equal 0 no matter what I plug in for x. So the only critical values I'm going to have are going to come from where the denominator is 0, from where the fraction is undefined. Looking at the denominator, 4x minus 8, if I set that equal to 0, add 8, divide by 4, I see that f double prime does not exist if x equals positive 2. So that does give us a critical value to work with. Let's put that on an f double prime number line now, so positive 2. And let me test something to the left of 2, like 0. Now, to test this out, there's a lot of different versions of f double prime. I'm going to use the most simplified version over here, the 128 over 4x minus 8 cubed. If I plug 0 into this, downstairs I end up with negative 8 cubed, which is negative. And combined with the positive upstairs, that gives me a negative overall result. Now let me try something bigger than 2, like 3. Downstairs, 12 minus 8 is going to be a positive. Combined with the upstairs positive is going to be a positive. Because f double prime is positive after 2, f is going to be concave up from 2 to infinity. And because f double prime is negative before we get to 2, f is concave down from negative infinity to 2. For this one, I'm just trying to find concavity intervals for this quartic polynomial. So for that, let me get the second derivative. Starting with the first derivative, though, we've got 4x cubed minus 3x squared minus 6x, and then that 2 is gone. We need one more derivative, though, f double prime. That's going to be 12x squared minus 6x minus 6. And if I set this equal to 0 and solve, I can begin by factoring out a 6. That'll leave me with 2x squared minus x minus 1. And now I'm going to try to factor this a little bit. So if I'm factoring this, there's really only so many possibilities. I need a 2x and an x, and I need some combination of positive 1 and negative 1. If you play around with it a little bit, you get 2x plus 1 and x minus 1, because 2x times negative 1 gives me a negative 2x, combined with the positive x I get by multiplying these inner factors, these inner terms here, and that gives me the negative x in the middle. So a little bit of guess and check. We factor that, and we see that we have critical values at, let's see, setting each of these equal to 0, we have negative 1 over 2 and positive 1. So here's my f double prime number line. Let me put those critical values on there. Negative 1 and negative 1/2 rather, and 1. Let's test something to the left of negative 1/2, like negative 1. And I'm going to use this factored version of f double prime. So plugging in -1, that's going to give me a negative and a negative, which is positive. Now a number between -1/2 and 1, how about 0? That gives me a positive times a negative, which is negative. And bigger than 1, I'm going to try 2. That gives me a positive times a positive, which is positive. Since f double prime is positive in the first and third intervals, that tells me that f is concave up from -infinity to -1/2, and also from 1 to positive infinity. And because f double prime is negative between these two critical values, f itself must be concave down between -1/2 and 1.